as small as a fragment. So by definition, fragment is somewhere around 100 Daltons and above, to small molecule, which is around 300 Daltons range, all the way to peptides, which is around 1,000 Daltons, to proteins, antibodies, and membrane proteins. So we currently do have a wide range of customers coming from academic, biotechs, and pharma and CRO using our instrument for anything from fragment library screening. They use a wave rapid feature, off-rate screening, to full kinetics binding characterization. So ultimately, with the instrument, you can actually get on and off rates, ultimately allowing you to calculate binding kinetics and also affinity. Okay, I want to show you a video about our wave technology, kind of to show you how we see light. So the technology behind wave system is actually called gradient coupled interferometry. So ultimately, we are an interferometry based system. So here I'm going to play a video. Okay, so there's a laser, which is the light source. It's going to shine light onto a sensor surface. So imagine on your sensor surface, you have antibody pre-immobilized on the surface. There is an internal reference light, which is always used as a reference. And then the detector at the bottom will collect, the signal. So the small balls, green balls, are basically your analyte. So during an association, as you flow these analyte across the surface, you're basically detecting the change in phase during binding interaction. And during dissociation, you're injecting buffer. So your analyte dissociate, and you actually is still monitoring the return of phase to its original state. So that's the definition of interferometry. So another static view. So how our GCI has increased sensitivity due to the way we sense light. So I'm going to admit this person. Nope. Okay, thank you. So just like in the video we showed earlier on the GCI, which is on the right-hand side, actually we fully utilize the entire sensor surface. So light can actually travel the entire sensor surface. Because of that, we can actually capture more binding signal, especially for small molecule binding. So in result, we have a higher accumulated binding signal from small molecule binding. As opposed to SPR, in traditional SPR, what you also have is a light source located below your sensor chip. What it basically does is shine light at an angle, and the signal you're collecting is actually only coming from a localized field. So in result, you can get smaller signal in SPR. I also want to show you, a video about how fluid flows on our sensor surface. So here is a video of just showing how sensor fluid flows on our sensor. Okay. So in this video, you'll basically see what happens during a kinetics interaction. So basically during baseline, the instrument will prep your sample in this loop, and it basically kind of flows at a reverse direction. And when it's ready to inject during association time, the sample is flow across the sensing area at a forward direction. And lastly, during dissociation, buffer is flow at the reverse direction. So this kind of forward, reverse, forward kind of orientation minimizes the dilution of your samples during the change in step. So this means that when you are actually doing association, injecting your sample across the sensor, you're actually seeing the actual concentration of your analyte without dilution. So it's quite important, especially when you're working with, let's say, really high or really low concentration. You don't get that kind of like dilution effect. I also want to point out with our instrument, this is actually a part of the consumable, which is called the wave chip. So there are actually parallel flows on these wave chip, meaning that there are 4 flow channels, a little difficult to see, but they are basically located at the black rubber for parallel flow. This means that your flow channels are not connected in series like traditional SPR, and all of your channels actually see solution at the same time. So there is no integrated valves in our system. So this allows our instrument to actually capture really fast transition time, especially when you're working with fragments, you're used to seeing really fast on and fast off interactions. We can actually capture really weak binders, let's say micromolar, high micromolar, and millimolar range binding affinity as well. All right. The next part I actually want to talk a little bit is actually the wave rapid feature, a quick way of running kinetics. This is actually a new software feature that was launched back in 2021 of January. So kind of to help customers who need higher throughput to go through a large sample size faster. So when you're running kinetic assay, typically what you have is you have a baseline, association, and dissociation step. So in a traditional way of running kinetics, what you have to do in terms of users, you have to prepare serial dilution of your analyte. And so then you will inject those different concentration of analyte across your sensor one after another. So this is what we typically call traditional kinetics on our software. And basically what you're doing in traditional kinetics is probing the interaction by injecting different concentration of analyte, but of the same injection time. So typically this is what you would see in one-to-one binding model, a really well-resolved on rate and off rate. And what happens is over time, as you inject higher and higher concentration of analyte, you actually reach saturation. So the software can actually take all of these signal that you collect in the experiment and fit it to this rate equation to solve for the KD, the Ka, ultimately allowing you to calculate binding affinity, which is K off divided by Ka. So in our rapid technology, rapid stands for repeated analyte pulses of increasing duration. So in this case, user actually no longer have to do serial dilution of your analyte. What you will have is actually single well analyte at high concentration, and the software will actually pick up that single well analyte and do pulse injection across your sensor. So by default, it will always do 6 pulses, and these pulses are of short to long injection duration. And the purpose is kind of to mimic the typical dose response you get from traditional kinetics. So the software can still fit, this signal that you get from wave rapid and fit it to the same day equation in order for you to calculate off rate, on rate, ultimately your binding affinity, but at a faster speed. So the cost benefit of using wave rapid. So depending on the binding affinity range of your sample that you're testing, if you're working with weak binder, let's say micromolar range, with the wave rapid, you can run up to 480 samples per day, as opposed to if you're using traditional kinetics, you can run about 60 samples per day. So that's about like 5 to 10 times faster than traditional kinetics. So you'll see the same trend when you're working with intermediate binders, which are the nanomolar affinity range in the middle of the graph here, or the really tight binder, picomolar range binder. You will actually be able to still run more samples with wave rapid when compared to traditional kinetics. So if anyone in the audience is working for screening, this is a feature you can actually look at in order to have higher sample throughput per day, so you can move along your project faster. The other thing to think about is if you're working in a plate format. So because you're no longer needing to do dilution, each of these well actually contains a sample. So let's say if you are prepping your sample in 384 well plates, each of these well is a sample. When you queue up a 2-day experiment, you can actually get 384 data set at the end of 2 days. So this is walk away time from the customer. So you just let the instrument run for 2 days, and at the end of the experiment, you can get a lot of data set. I also want to highlight, the capability of our easy to use software. So a lot of our wizards are available to customers. So they serve as starting point for customers to work with, let's say, a pilot project, or you want to do a quick screen. You no longer have to manually build a template for your assay. So wizards are available in picomolar all the way up to millimolar range interaction. It has some default settings to help you quickly set up an assay. And here's an example of screen where if you do a intermediate binding affinity settings, you can actually quickly pick up, differentiate if you have binders versus non-binders, if your analyte binds in micromolar range or nanomolar range, due to the way that you see the curvature on these wave rapid data set, basically. And then from there, you can always follow up with more assay to optimize your assay. And if you're interested to learn more about Wave Rapid, we do have a lot of free resources available. I also want to introduce you to our YouTube website. It does contain several or more multiple videos from our KOLs. They talk about how they currently use Wave Rapid in their projects in order to help them accelerate their project progress. There are also tech notes and also a white paper available to our customers. It's free resources. It shows benchmarking studies and also screening characterization results with Wave Rapid. All right. And then lastly, the last part that I want to talk about is the wide application that you can use your instrument for. We will not have time to cover all of the applications, but what we can do is actually show you a few examples for small molecule and also GPCR membrane proteins. And if you have any question, we can always follow up with you. So here is just a data set showing the sensitivity of the instrument. So on the left-hand side, this is a channel that is immobilized with high amount of carbonic anhydrase, our favorite protein, around 30 kilodalton. You can see that when you flow a small molecule across that high ligand surface density channel, you see very well resolved on and off rate, enabling you to solve for on rate, off rate, ultimately binding affinity. So if you're pushing the limit of the instrument where you use low amount of ligand to immobilize on the surface, you can see that even though you get really small signal right here, if you zoom into the right-hand panel here, you can still actually see very comparable on and off rate, meaning a really well-resolved kinetics profile. So if the software fit the data, again, you can compare the binding parameters from both sensorgram and see very comparable values. Here's another example if you're working with weak binders. So let's say you're doing fragment screening. Here's an example of, again, our carbonic anhydrase data set around 30 kilodalton binding with a fragment which is around 100 daltons. So again, it's a very common profile where you see a rectangular shape, fast on, fast off interaction. You can quickly see with a naked eye within a few seconds, your signal actually returns to zero. So it's hard to fit this, but our software is actually able to capture the off-rate signal and fit the data. And this interaction is defined as with the off-rate of around 3 per second and the binding affinity of high 300 micromolar affinity. I also want to point to customers or our audience. Our instrument can actually be used to work with non-purified sample. So here's an example of a minimally purified GPCR membrane protein. So we do know GPCR membrane protein are notoriously difficult to purify. And so let's say if you only have very limited amount of protein, what you can do is actually try to put it on our sensor and capture it on our surface. The example shown here is the GPCR membrane protein capture on streptavidin surface, which is in channel 2 in red, and then in blue is a negative control membrane without the protein. And then you can titrate nanobody to kind of quickly check activity. So same idea also applies if you're working with, let's say, protein expression in your lab, where you're interested to see what you're trying to express in early stage actually have activity, if it's worth your time to make more, or you need to optimize the construct. So all you really need to do is take your crude sample, give it a quick centrifugation, take the supernatant, and you can load it or immobilize it on the sensor and just do a quick kinetics on the instrument. So lastly, I also want to show you a comparison of wave rapid data versus traditional kinetics data. So this is actually a data set generated by one of our CROs in Europe, LeadX Pro. So they use our instrument for a variety applications. So on the left-hand side is actually a nanobody binding with a transporter. You can see on the top panel here, this is the wave rapid results that they were able to achieve with a reported KD of 23 nanomolar. So they did a follow-up assay with a traditional kinetics. They were actually able to see very similar binding parameters with a KD of 34 nanomolar. On the right-hand side here is actually an example of small molecule binding with GPCR membrane protein. So on the top panel here is actually, again, the rapid results, reporting a KD of 18 nanomolar. And the bottom is actually the traditional kinetic results, again, giving very comparable binding affinity around 24 nanomolar. So I just want to end here saying that, the wave rapid can be faster. It can also provide very confident binding kinetic at a higher speed if you need sample throughput. The last thing is just, tech notes. If you're ever interested in learning more about, how to use wave rapid or wanting to look more about data sets, we do have a lot of these resources available on our website, which is malvernpanalytical.com. All you need to do is go to our knowledge center and key in the appropriate instrument. In this case, you will key in GCI, which stands for gradient coupled interferometry, and you will have a whole list of technical notes and app notes. So feel free